Hi everyone, how's it going? For those of you who didn't make it to the tutorial, or for those of you who did and want to recap on stuff that we looked at, and also some of the things that we didn't quite get to during the tutorial, I'm making this little video of the tutorial problems. So let's get into it. I'll just share my screen. Okay, so you should be able to see on the screen now my PowerPoint for the tutorial problems. You can get the solution to the tutorial problems, so the PDF of these PowerPoint slides from the solutions page on Canvas. So let's work through this. Let's get this working. All right, so the first problem was relatively simple, just two gear gear train. We've got an input gear here, or a pinion, with 17 teeth, a module of 3, and a speed of 1150 RPM. So there's a few things in each of these problems as we work through that you should know something about from before, and in each problem I'll introduce something new. So one of the things that you may not have come across before is the module. So yeah, I dealt with that in the lecture video, so you can go back and review that if you need to, and also my lecture notes. Yeah, but from that, we've got the desired output speed of the mating gear is 560 RPM. So to achieve that, we need to determine the number of teeth for the gear. Okay, so I've just drawn the gears just as two circles, simulating the cylinders rolling on each other without slipping. But of course, these gears would look something like this, right? Just spur gears. Okay, so once we've done that, in machine design problem, these gears have to be supported somehow. So they would be mounted on a shaft, and those shafts would then be mounted in bearings, and those bearings would be in a housing or on some other frame. And you would need to specify for the machine design where those bearings have to be, right? And what tells us where those bearings has to be, or where those bearings have to be, is the center distance. Okay, so we need to work out what this center distance is. All right, so the first part, so I've called the first gear here gear number 2 and gear number 3. The reason I've done that, in some textbooks and some references, they'll call the first gear number 2 because it's actually the second, usually the second machine element in the powertrain. So number 1 might be a motor or a wind turbine going through to a generator, whatever, right? So there's usually something else in this machine that's the number 1 machine element. All right, so we're told this information, and we know from the lecture that I did before that the ratio of the speeds is inverse to the number of teeth on the gear. Okay, and the number of teeth on the gear is proportional to the radius or the diameters of the gears. All right, so from this equation, N2 is our input speed. We're given an output speed of N3, where we know what the number of teeth on the input is, N2, so we just need to rearrange that to find out what our number of teeth need to be. And our calculator tells us that we need 34.9 teeth. Now, hopefully, obviously, or intuitively, you can't have partial teeth. You need to have a whole number of teeth in a gear. So you have to decide whether to round up or round down. Which one do you do? Usually, to help you make that decision, in this case, we're pretty close to 35, so I think, well, let's just round up to 35 because that's the closest. But another thing that you can use to help you make that decision is often, or nearly always, the specified output is not an exact speed, right? It might be a speed plus or minus 1%, 5%, 10%, and that will tell you whether rounding up or down will do. Also, rounding up or down might give you an exact integer relationship. So 2 times 17 is 34, right? So, if my answer had have come out here to be 34.2, for example, I wouldn't have chosen a 34 tooth gear here, right? Because I would have had an exact integer ratio between the two gears, okay? And if I'm not going to go through that in this tutorial video, we talked about that in class, but if you look up hunting tooth or why you shouldn't use exact integer ratios, you can do that, right? But simply the reason is that it evens out the wear, right? So if you have an exact integer ratio, you get more where the same tooth comes in contact with the same other tooth on the other gear more often, right? So anyway, that's another decision you'll need to make from here. The other thing that might influence your decision is the stock gears that you have available, right? So if you go, right, I need 35 tooth gear, you go to the manufacturer's catalog and you'll find that they don't make a stock 35 tooth gear with a module of 3. It might be 32 and let's pick a number 40. Right? Which one do you choose? Okay. Then you would need to, you probably want to go smaller if you can, because it should be cheaper. Right? But you would want to check whether your output speed is within the allowable tolerance or variation that might be specified in the design specifications. All right, so we've just kept it simple here. Nearest whole number of teeth is 35, so we're going to use that. Let's check our actual output speed. So just rearrange this equation here, and we get 558.6 RPM. All right, pretty close. All right, so the next thing we need is the center distance. Okay, so we're not told any information about the diameters or about the size of these gears. Okay, so what we are told is the module, right? And the module is what we use in the metric system to define the size of the gear teeth. And then if you know the size of the gear teeth from the module and you know the number of teeth, you can calculate what we call the pitch diameter, okay, or the diameter of the pitch circle. And the pitch circle is a theoretical circle from which all other parameters are based when we're doing our calculations with gearing. Right? So, and the pitch circle is that theoretical circle where we've got two cylinders rolling on each other without slipping. Okay. All right, so I've said that all there, and this is the relationship that I showed you in the lecture. So the module is equal to the pitch diameter divided by the number of teeth. So from the pinion, we can calculate our pitch diameter as module times the number of teeth, which gives us 51 millimeters for our pitch diameter. For the gear, we have the pitch diameter equal to okay, so I'll just use the ratio of the teeth here to get that, because we know that the pitch diameters must be the same ratio as the numbers of teeth. Okay, so we've got 105 for our pitch diameter here. Alternatively, since the module must be the same for both gears, so that's another important point. When you have two gears mating, the module must be the same for both. So we have module 3 times number of gear teeth was 35, so we get 105, the same as we got up here. Right? And center distance, now we just got simple primary school maths, just the average of those two, or the sum of half of each diameter gives us a center distance of 78 millimeters. Okay. All right, that's that problem. So let's move to the next one. So a little bit more difficult. Now we've got lots more gears in our gear train. So from N2 to N3 to N4, we've got just a simple gear train. Then N4 and N5 are a compound gear train. So these two gears, N4 and N5, are both rigidly connected to the shaft. Right? So we might have a keyway in here, or as I showed in the tutorial with the physical example that I had, it was machined out of just one blank of material. Right? But however it's made, the concept is, or the idea is, that both of these two gears, gear 4 and gear 5, both rotate at the same speed. Okay, and then to our output, we've got just another mating pair of gears. All right, so the reason that we might do this is that we want to get a larger gear reduction or increase than we can get by just simply having one really small gear and one really big gear. So if you look back at the lecture notes, you'll see that there's limitations on the maximum gear ratio or velocity ratio, train value, whatever you want to call it, between one spur gear and the next. All right, so in this one, we've got an input speed of 100 RPM. All of the numbers of teeth in this case are all specified for us, and we want to determine the speed and direction of rotation of each gear, and then the overall velocity ratio. So firstly, we'll do this by working through each pair of mating teeth, and then we'll check the value that we get for the velocity ratio with the train value equation for just looking at the entire multiple gear train. All right, so let's do that. So our solution, so again, we're just using that simple equation that relates speed to, in this case, the number of teeth on the gears, because that's what we're given. We're not given, in this case, any diameters or anything like that. We're just given numbers of teeth. So our speed of gear 3, inversely proportional to relative to gear 2, is inversely proportional to the number of teeth. So we can just put that into our equation, and we get 48.649 RPM for gear 3. And as you would have seen in the lecture and in the tutorial, and just from past experience, that they'll rotate have to rotate in opposite directions. Yeah. Okay, so that's where the negative sign comes from. All right, so let's move to the next pair of mating gear teeth, and that's between gear 3 and gear 4. Again, we can use the same relationship, and then we can substitute from up here into there. What have I done here? Oh, and then I've just done here. All right, and the N3s cancel out. So this is an important point here, right? Right, this gear number 3 is an idler gear. So it has no effect on the velocity ratio between N2 and N4. Okay, so we could have made N3 any size we like. Right, in this problem, it's N4 is 20. Right, okay, so right, that's where right, so N4 here is hidden in here is 20, and N2 is 18. Right, so that's where the 18 over 20 comes from, because the N3s cancel out. Yeah, so N3 here was 37. We could have made it 10. We could have made it 57. Wouldn't matter in terms of the ratio or the velocity ratio between N2 and N4. Right, and then, but what it does do is to again reverse the direction of rotation from N3 to N4. So now N4 is rotating in the same direction as N2. Okay, so two reasons that we would use an idler gear. One is to separate the shafts, right? If we need to get some distance between this input and this intermediate shaft, or if it was just direct to the output shaft, we might put this in here to give us that separation. Or if we want this shaft here between gears 4 and gear 5 to be rotating the same direction as the input, then we'll put an idler gear. All right, so N5, as I said, it's rigidly attached to the same shaft, so rotates at the same speed. So N5 is equal to N4, rotating in the same direction because they're on the same shaft. And then from N5 to N6, we've got our gear pair relationship again. Substitute from up here, the N3s cancel out, and we get, putting in our gear teeth numbers from over here, we get an output of 55.4, and it's in the opposite direction to the input shaft. Okay, so having got our output speed now, we can calculate our overall velocity ratio by using input speed over output speed. Okay, remember, as I said, some people and textbooks and sources define the velocity ratio the other way, but I'm following the way that's done in the recommended or required textbook. So yeah, if we put 100 over 55.4, we get 1.81 as our velocity ratio. Right, so the next thing I asked you to do is to check the velocity rate, overall velocity ratio, by using the train value equation for multiple gear trains. So our train value is the product of the number of teeth in driven gears over the product of number of teeth in driving gears. Okay, so now we need to understand what driven and driving teeth are. Right, so if we look at gear 2 here, where it mates with gear 3, gear 2 is driving gear 3. So we have driving gear teeth 18 and driven gear teeth 37. Then when we move from N3 to N4, gear 3 also has driving teeth as well as driven teeth. Okay, so yeah, so down here where it engages with gear 4, we've got N3 driving teeth and N4 driven teeth. Now, N4, even though it's driving N5 through the shaft, there are no teeth that are driving. Yeah, right. The driving part of the power transmission or the torque transmission is done through the shaft. Okay, so N4 has no driving teeth, only driven teeth. And N5 is being driven through the shaft. So gear 5 only has driving teeth. It doesn't have driven teeth. And then N6 or gear 6 has N6 driven teeth. So if we put that all in, so on the top we have driven gears. So we've got N6 being driven, N4 or gear 4 being driven, and gear 3 being driven. Then on the bottom, driving gears, N2 is driving, N3 is driving, and N5 is driving. Okay, so we just put in the numbers and we get the same train value for the entire gear train. Okay, next one. So in these tutorial problems, what I'd like to do is to refresh stuff that we've done, and then on each new problem, introduce something new. All right, so now again, we've got a gear train shown below, and we're asked to determine speed and direction of rotation of each gear and the overall velocity ratio, but this time we're not given an input speed. Okay, so now we need to make use of the relationship between power, torque, and speed. Okay, and I went through that in the lecture. All right, so we know that power is equal to the torque applied times the rotational speed. Okay, remember, we're considering this in as constant rotating on a constant speed. So we have rearranging this equation, we get our input speed because the input power is given and the input torque is given. So this is our input speed. And if we put, all right, so this is one of those equations where you need to be careful with the units that you're using. So in the metric system, power is in watts, torque is in newtons and meters. Our speed comes out in radians per second. So you just need to make sure that you're right. So a mistake a lot of people make with this equation is to put in here for speed the RPM speed, right? So you need to convert RPM into radians per second. All right, so and I've done that here for you, okay? Right, so if we're considering gear 2 to be rotating anti-clockwise to start with, we can use that same thing that we've been doing for the last 2 tutorial problems to get the speed of N3. And from N2 to N3, it's just a simple gear pair, so the direction changes. From N3 to N4, we have a compound gear again, so N4 is just equal to N3 and rotating in the same direction. And then on N5, from gear 4 to gear 5, use that same ratio again to work out the speeds. And gear 5 is rotating in the same direction as gear 2. And our velocity ratio, just N in over N out. And we get this time a velocity ratio of less than 1, right? Because you can see that we're going from a big, slow gear through to a faster, small gear. Right? So our velocity ratio is 0.64. And I've left off here the train value. I'm just done here using the train value. So let's, I can never remember which one works, which way we do this. So driven gears on the top. The driven gears on the top. So driven gear, so N5 is a driven gear and N3 is a driven gear. Okay, so we can put those numbers in. N2 is driving N3, so N2 goes on the bottom, and N4 is driving N5, so N4 goes on the bottom here, and we get the same value for the train value as we get for the velocity ratio. Okay, so that's a quarter of a tutorial done, so let's see what we've got here. Yeah, let's go on to this one. Actually, I might stop the video here and come back and start again. Gives me a chance to have a rest. Gives you a chance to have a rest and think about what we've just looked at. All right, so see you in the next video shortly. Bye for now.